Let's hope this goes a little nicer. Hypothesis testing for standard deviation, SD. We get a new Greek letter, aren't we all excited? So fancy X is either a chi or a chi. I always called it chi. So this is a chi squared. And I always forget this formula because it's not one I use a lot. S squared over sigma squared. Technically, these are variance, but the variance is just standard deviation squared. So same thing. So S equals sample, standard deviation, sigma equals population, standard deviation. We have a degrees of freedom again, n minus 1. So really calculating the statistic isn't terrible. You're squaring things, multiplying, dividing. So you're just multiplying a bunch of stuff, really. So calculating that shouldn't be an issue. Pretty straightforward. The picture of this test, though, is kind of weird. So I'm going to bring up the slide rather than talk all the way through it. Whoops. Forgot to pull that up. Okay. So here's the characteristics of a chi-squared distribution. Things to note, it is not going to be symmetric. So it skews to the right. It's got a big camel hump to the left and then a long tail to the right. The shape is going to depend on our degrees of freedom. Our shapes, we're just going to draw whatever we draw as usual. The number of degrees of freedom increases, it's going to start to look more symmetric. And since we're squaring things, we're always going to multiply by positive numbers. We're going to have a non-negative, so greater than 0, greater than or equal to 0, excuse me, chi-squared. So we should not get a negative value out. If you do, you've made a mistake somewhere and go see what happened. They happen. So those are our big things. Do I have? Here are some pictures of different chi-squared. So each color line is a different chi-squared. The red one or orange one are most likely what we're going to use, like draw here. So, but you can see as we get higher degrees of freedom, this purple one looks pretty symmetric. So they shouldn't have drawn purple and blue like they did, but that's okay. So. Oh, we'll get there in a sec. So possible outcomes. We have a two-tailed. This is sigma. This equals, excuse me, sigma naught. And this is the same as before. So there's no difference. And honestly, these are going to look familiar. It's the same as they were with standard deviation, excuse me, mean, standard deviation now. So So our null hypothesis is always our sample standard deviation equals the population standard deviation. You're going to use table 8, which I will flip to when it's time. And if we reject versus fail to reject the null, this looks a little bit different. So give me a sec. I'm going to get this all scribbled out and then I'll talk about it. So a two-tailed test. We have three and a half different outcomes. Yeah, but if you look at the oh, never mind, I see the difference. Yeah, the subscript, that's what word I was trying for. We draw a sideways alpha. So for the two-tailed test, because we're always positive, we have to look at this a little bit different. My picture should be less symmetric than it is, but it's fine. So what the two-tailed test says, if we're in this zone here, so we look up that 1 minus alpha over 2. So it'll be like the 95% level or something like that. If we're in that zone, or we're over here, which is, if we're using the same idea, alpha over 2, so like the 5.05 zone on that side. So I can actually, I don't want that color. That is what percent of the graph is to the right of our value. So on the left, you have a lot more to the right than we do the right. Portion. Okay, so I'll scroll back up to look at the other ones, but so the blue numbers is the proportion of the graph to the right of the line we put there, the critical value. So that's why the number on the left is bigger than the number on the right, which is usually not the case of a typical number line. So it's not, we're looking at percents. So I think of it as the percent to the right of our line. For a left-tailed test, we just take that picture and look at the left side of it. So I'm going to draw one picture for both of these and label them. Here we go. So this is pi squared of 1 minus alpha. This one, we look at this area, and that is pi squared of alpha, which is this one. So by all rights, I should have drawn two pictures, one for the left, one for the right, but if we color code them, it works okay. And again, that is percent to the right of our line, of our critical line. These are really weird. It's counterintuitive, worse than some of the other things we've talked about with the intuitiveness. Again, I was a big picture drawer for any of these to make it make sense. Okay. I have one example, which I think is all we're going to have time for. Yeah. Can I scroll past? Do you need me to stay on the picture for another sec? I can wait. I can always scroll back when we're done too. Okay. No, oh, that is the slides. Okay. Here's our example. We are dealing with the quality control at M&M again. I want that job if I can snack on them. So we're supposing our standard deviation, our population one was 0.75 grams. And we want to figure out after we calibrated, is the standard deviation the same or is it significantly different? So I'm not going to have us calculate the standard deviation. Oh, I didn't even write that down, did I? Boo. We're not going to calculate the standard deviation. Actually, I'm going to go cheat. Where did I put the slides? No, we're just going to go with it. Okay, so, oh no. Okay. We have a one-tailed test and our critical value was 0.05. So we want, we have a left-tailed test since we're saying, is it less than? Because if it's less, that's the issue. So I forgot to write the standard deviation down. So we're just going to go straight to the test statistic, and I can look at this at the end too. Okay, so the test statistic that we found by calculating, we get 7.291. And if we look up our critical value, so it's our 0.95, and our degrees of freedom was 10. Okay, let's find our chart. Table 8. Okay, so degrees of freedom is 10. That is this bottom part of the orange box. They were nice to us. And we're looking up the 0.95. So I come to the top, my 0.95 at 10 gives me 3.940. So that's our critical value. We need to be farther from the center than that. So I draw my picture. And we have a left-tailed test, so if we're over here, we have a significant difference, we're saying. Now, how I have our stuff graphed, we actually have a number line at the moment. So our number, if this is 0 over here, is farther to the right than our test value. So call our number here-ish. $7.291. So we're not in the blue zone, we're not in the tail. We fail to reject our EJ, the null hypothesis, because we're not in the tail. So we don't have a significant difference. I suspect if we were to go to the high side that we would, but that's not what they asked us, so that's not what we're going to look up. Okay, I'm gonna stop my video there, and then I'm gonna go back and look at slide 143 and beyond to get our standard deviation, and then we'll just practice calculating the chi-square. That's shorter.